Today what I'd like to do is introduce two very important constants that you frequently would come across when you're studying kinetic theory of gases or gas laws. And those two constants are the universal gas constant and the Boltzman constant. And just to give some background information first, people found out experimentally that if you take any gas and you plot its PV product as a function of the gas temperature, then you would get a straight line. So for instance, if I was to take gas A, then I would get a straight line which I've labeled over here. And if somebody else was to take, say, let's say gas B, he or she would also get a straight line. And these two gases don't have to be the same; they could be different. The quantities could be different, but you would always get a straight line. And so if I have chosen my axes such that my y-axis intersects the x-axis at a point 0 degrees centigrade, which is the freezing point of water, then if I was to extend if both of us were to extend our straight lines to the left, then something very interesting would happen, which is that even though our slopes were different because we were using different gases and different quantities, these curves would intersect the x-axis at the same point, and you could repeat it with any other gas you like, any quantity, and you would end up with the same result, that you would get a straight line and the point of intersection with the x-axis would be the same. So it was found that this point of intersection corresponded to a temperature of minus 273.16 degrees centigrade. So for convenience, I can just go ahead and take my original x-axis and just move it to the left by an amount of 273.16 degrees, and then I would get a different y-axis, which I will go ahead and show over here. And all that I'm doing is I'm just shifting it to the left. And so what that means is that any temperature I was measuring with my old x-axis, I just have to add 273.16 degrees to it to get my new temperature. And so, for example, if I had 100 degrees centigrade on my old scale, my new temperature is just this length, which is 273.16 plus 100 degrees, or 373.16. So this new scale of temperature is called the absolute scale, and the unit of my new unit of temperature is Kelvin. So another way of saying the same thing is that 100 degrees centigrade is 373.16 Kelvin. And the reason I do that is it just becomes more convenient, and I make sure that all my curves pass through the origin. And this is the 0 Kelvin that I'm showing over here really corresponds to a true minimum temperature you can achieve, because clearly at this point the gas essentially has a 0 volume or it vanishes. And so this is more representative of what is happening in terms of the volume of the gas than my old scale, which just used water as a reference point, the freezing point of water, to define what my 0 degrees was. And now, since my pressure times volume product is linearly dependent on temperature, I can go ahead and write a simple expression. My P times V is proportional to temperature, and this temperature I'm talking about is not my old scale, but my new scale, or the Kelvin scale. Now, this is not the only thing the pressure times volume is dependent on, right? This is also dependent on how much gas I have, or how many molecules or atoms of the gas I have to begin with. For example, if I use double the number of molecules of a gas, my P times V product will also fall in a straight line, but the slope would be much larger than what it was in the beginning. And so if I denote the number of molecules of the gas by the capital letter N, then I can go ahead and also write this expression, P times V is proportional to N. So I can combine these two and just go ahead and quickly write down P times V is the number of molecules of the gas multiplied by the absolute temperature of the gas. And or I can just introduce a constant of proportionality and say is times k times n times t, and it's this constant of proportionality is called the Boltzman constant. And what is very important about this equation is that it is not necessary for me to know what gas I'm talking about. This relationship is true regardless of what gas it is. So all I really need to know is how many molecules of the gas are present and what the temperature of the gas is, and that information is enough for me to calculate what the PV product will be. And so it's independent of the identity of the gas. Now, and typically when we talk about number of molecules of the gas, we are dealing with extremely large numbers. And for example, 2 grams of hydrogen molecules will have 6 times 10 to the 23 molecules of hydrogen. And similarly with 4 grams of helium, they will have 6 times 10 to the 23 moles. 6 times 10 to the 23 atoms of helium. So it's not very convenient to deal with such large numbers, and so just for the sake of convenience, people have introduced a quantity which is called a mole. So it's just a unit that is used to quantify how many atoms or molecules are present in a gas. And so the number of, okay, let me rewrite that. So 1 mole is just a quantity which is equivalent to 6 times 10 to the 23 atoms or molecules of the gas. And a simple analogy for this is that if you were to go and buy eggs, then you would buy a dozen or half a dozen, and you would not say, I want 6% of 200 if you want to buy a dozen eggs, because a dozen is a very convenient unit of measure, because that's typically what people buy. And when you're dealing with quantities of gas measured in terms of the number of atoms or molecules, then you're dealing with very large numbers, and so using moles becomes more convenient. And so if 1 mole is 6 times 10 to the 23, then if I want to calculate the number of atoms or molecules of the gas, then I can just say that the number of atoms and molecules is number of moles times 6 times 23, and this number is designated by, this is called the Avogadro's number, which I will designate by n sub Avogadro. And so the number of molecules or atoms of a gas is simply the number of moles of the gas multiplied by Avogadro's number. Now I can go ahead and plug this value of n in my original equation and just go ahead and say PV is K times n now is just number of moles times Avogadro's number times temperature. And I can define a new constant which I will call R, and I can define it by saying R is just K times the Boltzman constant times Avogadro's number. And after I do that, then I can rewrite my expression and just say PV is number of moles times my constant R times temperature. Now this is the universal gas constant, and once again it's independent of what gas I'm using, and this equation is called the gas equation. One obvious question is, why did people select this funny number 6 times 10 to the 23? They could have selected any large number they wanted, but it's more of a matter of convenience, because 1 gram of hydrogen has these many atoms of hydrogen in it. And so it was just a convention that we have followed till this day. So thank you so much for listening, and I hope this was useful.